Okay, we're taking a look at 2018's AP Calculus free response question. The first one we're going to take a look at today is number 4. So the height of a tree, we're given a table for this one, but the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Select values of h of t are given in the table above. In part A, use the data in the table to estimate h prime of 6, and then using correct units, interpret the meaning of h prime of 6 in the context of the problem. So, h prime of 6, part A. Remember, h prime of 6, that just represents the derivative. So we're trying to find the derivative of h at 6. Now, we don't have a function for h, but instead what we have is a table. And 6 is not given in the table. So instead what we're going to do is we're going to look at where 6 would fall, and 6 is between 5 and 7. And then remember that a derivative is really just a slope. So what we're going to try and do is estimate the slope at 6. Okay? So to estimate the table, or estimate the slope at 6 using the table, what we'll do is we'll do h of 7 minus h of 5 over 7 minus 5. From the table, h of 7 is 11, h of 5 is 6. So we'll take 11 minus 6 in the numerator, and on the bottom, 7 minus 5 is 2. 11 minus 6 is 5, and so my answer here is 5 halves. Now to interpret in the meaning of the problem, to interpret in the context of the problem, h is measured in meters, and t is measured in years. Okay, so what we're going to do is we're going to try and take a look at this. H of 7 and h of 5, those are measured in meters. The 7 and 5, that's the time, that's years. So I would say that at time t equals 6, the tree, we are talking about a tree, right? Yep, the height of a tree and then since my slope is positive, it's going to be increasing. And derivative is a rate, so increasing at a rate of 5 halves meters per year. Okay? All right. Part B. Explain why there must be at least one time t for t between 2 and 10 such that h prime of t is equal to 2. Okay, so because I'm given an open interval here, and because I'm trying to show that a derivative value is equal to something, okay, this is an MVT problem. Whenever you're trying to show or explain why a derivative must equal a value, think MVT. Okay. So for MVT, we need to show that the function's continuous and differentiable. So I would start by saying because h of t, and let's see, does it say anything about it being continuous? It does say it's twice differentiable. So because h is twice differentiable, it's also continuous. It is also continuous on 2 to 10. Okay, and we can apply MVT. So we're looking for somewhere between 2 and 10 to where the slope is 2, because we want to show somewhere where h prime of t is equal to 2. So we're looking for somewhere where the slope is 2. So let's go up to the table. We're looking for somewhere where it's 2. Let's see. 1.5 to 2 is only a half increase. We're going up. It looks like we're going up a half, but we're going up 1 in the numerator there. So that doesn't work. 0.5 divided by 1, that's not going to be 2, so that interval won't work. What about from 3 to 5? From 3 to 5, we'd have 6 minus 2, which is 4, over 5 minus 3, which is 2, and that's 2. So right now, the 3 to 5 would work. From 5 to 7, 11 minus 6 would be 5 over 7 minus 2, which is 11 minus 6 is the 5, and the 7 minus 5 is the 2. That's what we did in part A. That was not a slope of 2. And then for this last one here, 15 minus 11 is 4, 10 minus 7 is 3, so that one doesn't work. It looks like the interval from 3 to 5 would give me a slope of 2. Okay, so let's go ahead and show some work for that. So I would show that h of 5 minus h of 3 over 5 minus 3. And h of 5 from the table is 6. Let's clear up some of this extra work here. H of 5 is 6. H of 3 is 2, so 6 minus 2 on top. And 5 minus 3 on the bottom, so 4 over 2, which is 2. Okay, so there exists, and I would put therefore, there exists a t such that h prime of t is equal to 2 on 3 less than t less than 5. Okay? All right. So that's an MVT problem. Part C. Using a trapezoidal sum with the 4 subintervals indicated by the data in the table, approximate the average height of the tree over the time interval 2 to 10. So average height, that's just an average value. Because the height is the h function, that's a value. Okay, so the values here are the heights of the tree. So what we need to do is figure out the average value of the tree. Average value is integral over interval. So what we're going to do is we're going to take the integral from 2 to 10 of h of t. Okay, and then we're going to divide by the interval. Now remember, dividing by the interval is the same as multiplying by 1 over that interval, so 1 over 10 minus 2. Okay, and we're going to use a trapezoid rule to calculate this. So 1 over 10 minus 2 is 1/8. And then for the trapezoid rule, with 4 subintervals, remember the area of a trapezoid is 1/2 the sum of the bases times the height. And the bases this time are going to be the function values, and the height will be the width of the interval. Okay? So 1/2 times, in the first one here, let's get rid of some of this. In the first one, we're going to add the bases of 1/2 plus 2, or 1 1/2. Let me rewrite that. 1.5 plus 2, and we're going to multiply by its width. So its width here is just 1. Okay. Plus 1/2. On the next one, we go from 2 to 6 for the heights, and then the width is just going to be 2. So I'll take 2 plus 6 and multiply it by 2. Plus 1/2. Let's take a look at the next one. 6 to 11, so 6 plus 11, and then this one also has a width of 2. Okay, so 6 plus 11, times 2 plus 1/2 times, on this next one here, I'd add the two function values, 11 plus 15. And then the width on this one is 3. Okay? Alright, so we're going to simplify this, add them together, simplify it as much as we can without the use of a calculator. So it looks like they all have this 1/2 in common. So I'm going to go ahead and pull out the 1/2 with the 1/8. So that would be 1/16 that goes out in front. And then 2 plus 1.5 would be 3.5. 2 plus 6 is 8. Times 2 is 16. 6 plus 11 is 17 times 2 is 34. 11 plus 15 is 26 times 3. 26 and 3, 8, 78. Okay. So let's see what we've got. So 1/16 of 3.5 let's see, 3.5 plus 16 plus 34 plus 78. So let's see, 3.5, 16, 34, 78. The 0.5 would carry through, and then 3 and 6 is 9, 10, 11, 12, 13, and 8 would be 21. 2, 3, 4, 5, 6, 13, 131.5. So we've got 1/16 of 131 over 5. Because you don't necessarily have to simplify your expressions, this would be okay. Let's just practice going through these and simplify it as much as we can. So I would rewrite this as 131.5 over 16. I want to try and simplify these fractions as much as I can, or at least get rid of the decimal on top of the fraction. 131, I'm going to multiply the top and bottom by 10 to move the decimal over 160. Now, these are both divisible by 5. 13, 15 divided by 5. Let's see, that goes in there twice. 10, 3, 1, 6, 30, 15, 3. So 263. And then 160 divided by 5. 3, 15, 1, 0, 32. So the average value, and that can't be reduced any further. So your average value here is 263 over 32 meters. So if you wanted to kind of formalize it, put a last statement here, the average height of the tree from 2 to 10 is 263, meters. So 263 divided by 32 meters. Okay? Okay, let's take a look at part D. So the height of a tree in meters can also be modeled by the function g, given by g of x equaling 100x divided by 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? Okay, so let's kind of break this down and figure out what's given to us. given by g of x, that's the new height. Okay, so this represents the height, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So increasing means it's a positive rate. Rates are just your derivative. So what this is saying is that because x is the diameter and the diameter is increasing, then the derivative of x, so x prime at 50 is 0.03. Okay? According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So when it's 50 meters tall, okay, so let's see here. So I want to figure out the rate of change of the height. The change in height is given by g of x. And so if I want that rate of change, I want to take the derivative of this with respect to time. Okay? So when we take the derivative of this, we're going to take the derivative of g, and we're going to multiply it by the derivative of x with respect to time. Okay, so this is like a chain rule. This is like a related rates problem. So we've got to figure out what g prime of x is equal to, and then we've got to figure out what the derivative of x with respect to time is. Okay, so the derivative of g is 100x divided by 1 plus x. So we're going to need to take the derivative of that. So the derivative of that's going to be a quotient rule. So it's low times the derivative of the high. The derivative of 100x is 100. Let's write that function down here. So 100x over 1 plus x minus the high, 100x, times the derivative of the low, which would just be 1, all over 1 plus x squared. Now dx dt, that is the rate of change at a specific value. So we're not quite ready to put in a value for that, but we will be here in a little bit. Okay, so it says that x is the diameter of the base of the tree in meters when the tree is 50 meters tall. Okay, so when the tree is 50 meters tall, that's also what I want to figure out at the end of this problem. What is the rate of change with respect to time when the tree is 50 meters tall? So I need to figure out the diameter to continue with this problem, because the x here represents the diameter, it doesn't represent the height. So I need to figure out when is the tree 50, or what is the diameter of the tree when it's 50 meters high. So what we'll do is we'll set the equation of g of x equal to 50 and solve it. Okay? So 100x equals 50 times 1 plus x. 50 plus 50x, 100x, subtract the 50x. X is equal to 1. So what we're going to do is we're going to take this number and plug it in for the x's. And then when the tree is 50 high, it's changing at a rate of 0.03. Okay, so we're going to put those numbers into those places. Okay, so 1 plus 1 times 100 minus, let's see, 100 times 1 all over 1 plus 1 squared times 0.03. So 200 minus 100 over 4 times 0.03. 200 minus 100 is 100 over 4 times 0.03. Let's see, 100, I'm going to multiply straight across on this one. So that would get rid of the decimals, so that would just be 3 over 4. Okay? So the 3 over 4 represents the rate of change of the height with respect to time when the tree is 50 meters tall is 3/4 meter per year. Okay? That one's a doozy. I can go back over it if you need me to. Let me know.